Hello students, welcome. Professor Henkle here, happy to share all about the wonders of the chemistry of our oceans. So, in today's lecture, I am here to express how amazing Earth's water and its unique properties are, and how those unique properties set us up for some of the truly incredible features of our ocean environment in regards to dissolved solids, into nutrients, into buffering, and how that's going to tie into giving us a stable atmospheric climate. It is amazing what we have to get into today, and I am so excited to share this with all of you. So here we can see this is the oceanography, the chemical oceanography lab from San Jose State. Here are a couple college students who are monitoring and measuring. It looks like they have a very fancy device here to measure ocean salinity with depth. That varies. We'll get into that. And it's really great because I would like this to highlight that you could be a chemical oceanographer. You could study the interesting characteristics of the chemistry and how it relates to biological systems, to geological systems. And if you like what there is today, please contact me, let me know. We will get you connected. There's great resources and great institutions out there where you can do groundbreaking science just like this. Okay. Whole laundry list of what we're getting into today. We will look at the unique properties of water. This is one of the biggest, most important, most exciting parts of our lecture. We'll describe hydrogen bonds, how they affect water's properties, define the concept of outgassing, and tie that into the origin of Earth's water. We'll look at residence time, discuss salinity, how it's measured, how it's calculated, identify the 6 major ions in seawater, talking about the rule of constant proportions. We will dive into why salinity changes with, these are the big 2, latitude and depth. We'll identify the processes responsible for dissolved gases, the importance of those dissolved gases, including oxygen, carbon, and nitrogen. And then we'll look at carbon dioxide as a buffer in the ocean, and then round out our discussion on ocean acidification, what it is, and why it is important. Okay, so water. It's the most obvious feature on Earth. This is the blue planet. As observed from outer space, water covers 70% of our globe. And water makes life possible. Without water, as far as we know from anything that we have ever seen, discovered, understood, there's no life without water. And so thank you, water, for being here. It's ubiquitous. It's easy to be taken for granted. But no, water has unique, special properties in its chemistry that allow the oceans to be what they are, that influences atmospheric and biological systems. And then water is so cool all the way down to its atomic level that the way that the hydrogens and the oxygens bond together and the way that water molecules bond together with each other helps to provide all these great characteristics, of which we'll get into. So here is number 1. The number 1 interesting property of water that is unique to water in and of its own is that it is a solid, liquid, and gas at room temperature. So there's water vapor in the atmosphere, there's ice in glaciers, and there's liquid water on Earth. All 3 of these through the normal range of temperatures that are experienced on Earth's surface. Other similar compounds do not do this. Rocks are solid at Earth's surface. And, deep down underneath the surface, it takes incredible temperatures for them to melt into molten material. But water, being what it is, and shaped the way that it is, has this extremely unique property. Okay, so the question is, why does this happen? Why is water so unique? And the answer has to do with the shape of the water molecule. Now, this is absolutely amazing. H2O, two hydrogens, one oxygen, are sharing electrons to form a molecule. In this molecule, the orientation of the hydrogen is offset, so they're both on one side, and they're separated by about 105 degrees. Now, it is this bent shape of the water molecule that gives it such unique properties. But not only that, water is also a polar molecule, which means that there's a small negative charge on the oxygens. There's a small positive charge on the hydrogens, and these opposing charges attract each other through this very unique pattern of hydrogen bonding. Now, there's not a lot of substances in the world that have hydrogen bonds, and this is one reason why oil and water do not mix, even if you separate, if you've like stirred them up all together. Well, it's because the water and the oil, the elements don't actually bond together. So those two stay completely separate. Please watch the video on hydrogen bonds associated to learn more about this very unique process. You will also see the example of the olive oil and the water in this video. So please go there, check it out. Okay, now water has a lot of unique properties. This one may be my favorite. This is water's high heat capacity. So what the heck does this mean? Well, basically, this means that water is really difficult to heat up or to cool down because it has a great heat capacity. It can absorb a lot of water. So here I have a water balloon, and this is a lighter. You will see I have a video on this also, but hey, what the heck? I've got this in front of me. Let's just do this right now. So as the flame touches the balloon, the heat from this flame goes directly into the water. The water absorbs it, and therefore the balloon does not melt, it does not burn, it does not pop. No, in fact, the high heat capacity of water means that the water absorbs heat without changing its temperature. A lot of heat has to go into it for water to change its temperature. And this is the heat capacity of water. We can see a bar graph of various substances. What I want to highlight here for us to notice is that water has an incredibly high heat capacity: quartz, sand, and granite. What are those? Continents, land. Land has a lower heat capacity. So if you are at the beach on a hot day, the sun will heat up the sand so hot sometimes that your feet will burn. But the sun doesn't heat the water up that's right next to the sand, at the ocean this is, because the water has a high heat capacity. It can absorb a lot of heat without changing its temperature. Now, there's another quality of water called latent heat, right? And this is the amount of heat required to undergo a phase change from liquid to solid or liquid to gas. And the way that I can exemplify this is, now imagine you have a block of ice and it's 112 degrees outside. It's roasting. Goodness gracious, it's so hot. But you go outside and you take this block of ice, and that ice, it sits there. And it absorbs heat. That ice, it doesn't just melt. What's going on there? Well, it's absorbing heat without changing phase. First, it has to absorb an incredible amount of heat, and then the phase change occurs. You also know this when you boil a pot of water. You put the pot on the stove and you turn it on. Maybe you have gas, maybe you have an electric oven, however the method of heat transfer is there. The water starts to warm up. But before it starts to boil, it has to absorb an incredible amount of heat for that to happen, to change from liquid to vapor. So these are called, or this is called latent heat, the heat required. And whether we're going from ice to liquid to gas, or gas to liquid to ice, is going to change the name. So I'm not a fan of all text slides. I apologize for this, but to get these definitions in one place, here we go. Latent heat of melting and vaporization, latent heat of evaporation, condensation, and freezing. Now, these are basically the heat that it takes to move from one phase to another in either direction. So without going too far into these, the concept I really want you to know is when ice gets to zero, it doesn't just melt into liquid. It absorbs heat before that phase change occurs. And then, before liquid water can turn to water vapor, it has to absorb a whole heck of a lot of heat, about 500 calories per gram. Same thing in the opposite direction. For water to condense into liquid, it has to lose a lot of heat. The temperature drops, and then the same thing, a lot of heat has to be absorbed out of it, or released, that is, before liquid water will freeze into ice. So, exciting, important, unique property number 2, water's high heat capacity. What this does is it creates marine effects and continental effects. Land heats up, cools down. Water stays relatively stable. So if we look at the day minus night temperature, this is the temperature range, we can see that oceans exhibit relatively no change from day to night, and then land experiences significant change from day to night, because land areas have a much greater range of temperature from day to night during different seasons, where oceans moderate the temperature changes from day and night throughout all the seasons. So this is why it's 112 degrees at home. You're like, whew, oh my goodness, what am I going to do? I got to get out of here. Where do you want to go? Let's go to the beach. Why? Because of the marine effect. Oceans are moderating temperature, and we know that whenever we go to the beach, it's a lot cooler. It feels the temperature is much lower. We can find a little respite from enduring the hot temperatures that have been coming our way through Central Valley summers. Water is a solvent. So this is the important property number 3. Water is known as the universal solvent because of the unique properties of the polar molecule. Here we go again, chemical oceanography. Let's talk about this. The polar molecule has an oxygen, 2 hydrogens, positively and negatively charged. It can dissolve ions like sodium chloride really, really well, where you have an Na plus and a Cl minus. Na plus, Cl minus. And essentially, the water will dissolve, dissociate, and then as we can see here, it can surround and bond, keeping that ion in solution bonded to the water molecule. This is an amazing feature of the oceans. This is kind of the nuts and bolts of how the oceans are salty, and we'll talk about more why the oceans are salty here coming up. So, number 3, water is the universal solvent. Number 4, the solid phase is less dense than the liquid phase. Solid is less dense than liquid. Essentially, what we're saying here is that ice floats, and it's a really good thing that ice floats, because if ice sank, then all the water, all the frozen sea ice would sink to the bottom, and it would accumulate. And then it would accumulate, and it would accumulate, and it would accumulate, and accumulate, and so on and so forth, until the oceans were frozen, and then there's no life living in the frozen oceans because they're frozen. And so thank you, water, for the way that you bond in these frameworks, where when you have free floating molecules into weakly bonded into framework bonded, the density of water actually decreases. Water, fresh water, is about 1 gram per cubic centimeter. Ice, 0.92 grams per cubic centimeter. So and this is very unique to water, because most substances are more dense in solid form than less dense. Water, on the other hand, freezes, and its solid form is less dense than its liquid form. Thus, ice floats. Thank you, water, for your solid being less dense than your liquid. That's awesome. Okay, number 5. Water has a very high surface tension. There's capillary action on the top. If you've ever filled up a cup of water too full, you'll notice that there's a little dome shape on top. And this is because there are attractive forces below the surface of water. They are equally distributed in every direction. At the top of the surface, the attractive forces go into the mass of water. What this does is it gives an elastic skin that allows aquatic organisms to rest on top. Some birds can sit right on top of the seawater. What the heck is going on there? Well, that's because water has a high surface tension. So again, thank you, water, for your very unique characteristics. Now, let's review that real quick, actually. Okay, so water is amazing. We'll put our number 5 on here. And then now I get to build the case of why water is so incredible. Okay, so number 1, water exists through normal surface temperatures in a liquid, a solid, and a gas. That's amazing. Number 2, water has an incredibly high heat capacity and ability to absorb heat. I think I could just leave this on for the rest of the lecture, but nope, we got to keep going, so let's keep going. Number 3, water is a universal solvent. It can dissolve a myriad of different substances, like putting sugar in your coffee or powdered drink. Right? The whole reason that we have powdered drinks is because of this unique property of water, that it is a universal solvent. We've got the solid phase, less dense than the ice phase. Ice floats. Let me restate that. The solid phase is less dense than the liquid phase, meaning ice floats. That's so cool that ice floats. Thank goodness. I am just so personally happy that ice floats. And also, the surface tension of water is extremely high, allowing for an elastic skin to develop on the top. Okay, so where did all this water come from anyways? Well, let's go way back. The origins of Earth around 4.5 billion years ago. The late heavy bombardment through this period was bombarding, for lack of a better word, the Earth with comets that had ice. The Earth was differentiating into its compositionally distinct layers of core, mantle, crust. Plate tectonics were beginning, and the movement of heat and material through Earth's interior led to volcanoes. Those volcanoes erupted and outgassed water into the atmosphere, and over about 500 million years, that water was able to collect condense, precipitate, and form pools on the surface of the Earth that we now call Earth's oceans. It's a fantastical story, and I love thinking about the origin of Earth and the origin of the oceans. So as water began to fall, there was water everywhere. Water in the atmosphere, water in the oceans, water in the ground, water frozen on top of mountains, water in lakes, water running over the river, water in vegetation and soils. And so we call the movement of water through the Earth system the hydrologic cycle. Really amazing that this exists. Thank you, Earth's early oceans, and thank you to our dynamic Earth for having this complex system that helps support and sustain all life on Earth and you and I. So there's a lot of water on Earth. Where exactly is it? Okay, if we talk about the distribution of water and land, we've got 70% water, 30% land. Let's take that land out. Let's look at just the water on Earth. Of all of Earth's water, 97% of it is in the oceans. That's a lot. The 3% remaining is fresh water. So 97% salt, 3% fresh. Of that 3% fresh water, about 2% is locked in glaciers, continental and alpine, trapped in sea ice. It's all frozen, so inaccessible to humans for potable and municipal consumptional uses. About 1/3 of that 3% is stored in the ground, leaving very trace amounts left for people to use. Now, I have a great demonstration of this in the Earth Apple demonstration. Please watch that video, check it out. It's going to blow your mind to think about how little water is actually available to humans to use as freshwater resources. Okay, so we talked about how cool water is, its unique properties, where water came from and how it moves around the Earth. Now let's talk about the salinity, the total amount of dissolved solids and dissolved gases that are located in water. So when we're thinking about salinity, we can give it a percent. The average ocean salinity is about 3.5%. We can also express it as a part per thousand. So ocean salinity is about 35 parts per thousand. Now, we've been throwing these terms around: ions, compounds, molecules. What exactly are these things? Well, the ocean has ions. An ion is an atom or molecule with a net electric charge. The water molecule is an ion because it is polar. It has electric charge. There's other ions in the ocean that are really important. The big six: chloride, sodium, sulfate, calcium, potassium, and magnesium. 3.5% of the ocean is dissolved solids and gases. Of that 3.5%, we have the big six dissolved ions: chloride, sodium, sulfate, calcium, potassium, and magnesium. And we can see the relative proportions in the ocean of the big six. These are all conservative ions because the proportion doesn't change. So it goes a little something like this. The rule of constant proportion states that if I have a sample of seawater that contains 2% salinity, in that 2%, we will have 55% chloride, 30% sodium, 7% sulfate, 3% magnesium, 1% calcium, 1% potassium. If I have a sample of ocean water that is 5% salinity, of that 5% salinity, 55% will be chloride, 30% will be sodium, 7% will be sulfate, 3 magnesium, 1 calcium, 1 potassium, and so on. So what this says is that the proportion of the ions of these 6 major ions in seawater, no matter what the salinity, are constant. They're always going to be the same. The proportion, the relative abundance of one relative to each other. So let's think about the residence time, the length of time a single atom of an element remains in the ocean before it's removed. And so the residence time for chloride is 100 million years. That's a very long time. Chloride is by far and large the largest percent of ions by weight because it has the largest residence time. So residence time and relative abundance, sodium 30%, sodium 68 million years, calcium, so on and so forth. So what this does, having ions that have such long residence times, is it creates steady state conditions where the amount coming in of ions that are entering and the amount of ions that are exiting are equally balanced with the length of time that the ions can remain in the oceans to give us these relatively proportional constants, and also to create an environment of stability. And that stable environment actually started right around when the oceans did. This is amazing. Our dynamic Earth 4 billion years ago came out and said, I want some oceans. It's not a person. The Earth doesn't have wants. I will create oceans through the outgassing of volcanoes, and thank you, arrival of comets, and through this we will precipitate oceans, and they will have dissolved solids in them. And the relative proportions of dissolved solids has remained pretty stable over the past billions of years, as we can see identified in the rock record, because rocks, what is this, just some stupid rock? Don't say that. Rocks are really, really important because rocks are like the Earth's history pages. They tell us what's happened in the past. They tell us about the salinity of the oceans in Earth's history. But let's not get too excited about geology because we're excited about oceanography, and let's keep this going. There's ways of recording and measuring and observing. Our technology is great, and so measuring salinity can be done by hand from a handheld refractometer. This is quick. It's not the most precise, but it can give us an idea of point observations. A specific point in the ocean, boom, measure, that's what it is. More accurate are going to be with the conductivity probe. That's going to measure the electric potential that will give us a surrogate for the dissolved solids. We've also got large-scale salinity measurements using satellites. So cool. Satellites are amazing. They're all over the Earth, swooping around, recording all kinds of data, and incredibly valuable for our understanding of how Earth systems work on a very global scale. So where did this original salinity of the oceans come from? Well, it happened from outgassing of the water vapor. The oceans have always been about as salty as they are now, and the balance remains the same through the entry of runoff volcanic activity and hydrothermal vents. Ions can be removed through biological processes, sediments, and sea spray, and then hydrothermal activity. So we've got a whole variety of processes. But again, it's basically ions come in and ions enter, and they are balanced. So one of the big ways they enter is the silicate weathering system, which basically is when it rains on land, it erodes rocks. Or rocks break down and are transported through rivers, delivered to the oceans. Underneath at the surface at mid-ocean ridges, we have black smokers where Minerals in Earth's crust are released into the ocean by dissolving through these superheated cracks in Earth's crust. Really amazing process. I've talked about it before. We'll go in depth even more. So, salinity can vary all the way to hypersaline, the Dead Sea. Please see video of the Dead Sea, where you have an order of magnitude higher concentration of salinity into brackish waters. And what are the processes that could create more saline, hypersaline, or less saline? Input of fresh water basically will dilute. Temperature can change, and that can really lead to the amount of evaporation or precipitation. And temperature can also contribute to the development of sea ice or the melting of sea ice. So here's our video. Please be sure you check this in the video section. This is the Earth. Latitude, 0 degrees the equator, 90 degrees south and north. So let's think about this. Is it hot or cold at the equator? It's hot, yes. Is it hot or cold at the poles? It's cold. Okay, intuitively we know this. So red line, temperature. Cold at the poles, hottest at the equator, cold at the South Pole. So North Pole, equator, South Pole. Now, salinity varies with latitude also, but a little bit differently. The equator is hot. There's a lot of precipitation. The tropics are dry. This has to do with atmospheric circulation, Hadley cells. We'll talk about that in our ocean circulation chapter. Really great stuff. I love this topic, but the tropics are dry. There's a lot of evaporation. We talked about in the last slide, if we pull water out, it increases salinity, and if we put water in, it decreases. So, rainy, decrease. Evaporation, increase. We get this double hump of salinity, where the maximum salinity, the highest salinity, is going to be at the mid-latitude, specifically around the tropics. So here we get latitudinal variability. We have global sea surface salinity, and we have net precipitation. Now, green is high net precipitation around the equator. Take this over to a little bit lower salinity, mid-range here. Now, net evaporation right here, tropic. Take this over, right? We're going to have lower salinities here and here. So again, what do we see? We see the salinity at the tropics a little bit higher. I think I misspoke. Let me do this one more time. Higher precipitation at the equator, right? So the equator is hot. There's higher precipitation. Now, here we go. Salinity right around 35 through here. So our salinity, 35 at the equator. Now, let's go down here to the tropic, 37, 38. This is where there's net evaporation. So what these two graphs show us is that where there's net evaporation, we have higher salinities. Where there's net precipitation, we have lower salinities. So there you have it. Not only do we understand this process, but we can observe this phenomenon by recording measurements of both sea surface salinity and global precipitation and evaporation differences. So this isn't the only way that salinity varies. It also varies by depth. So we just said in that last discussion, high latitudes have lower salinity than low latitudes. High latitudes have lower salinity than low latitudes. These are the low. These are the high. Now, there's a mixing layer in the upper 200 meters of the ocean. And then below that, we have what's called a halo line. This is an abrupt change with salinity at depth, where high latitudes increase, low latitudes decrease, and then they line up for a deep ocean salinity that is globally constant. Cool stuff here. So we've got latitudinal variation and variation with depth. This takes us into our next discussion of how cool oceanography, the chemistry of the oceans are. So not only is there dissolved solids, but there's also dissolved gases, specifically oxygen, nitrogen, and carbon. And when we think about this, what's the atmosphere? 78% nitrogen, 21% oxygen, 0.04% carbon. What are the dissolved gases in the ocean that are important for life? Nitrogen, oxygen, and carbon. It's like somehow the Earth thought, hey, if I'm going to evolve and I'm going to evolve life, let's just use the materials that are available. And that's exactly what we see. So oxygen is really important for the respiration in marine plants, algae, and phytoplankton in animals. Carbon dioxide is used by primary producers to power photosynthesis. Nitrogen is primary production, is a nutrient that is required for primary production also. So not only is there oxygen, nitrogen, carbon in the atmosphere, it's in the oceans, and it's in the biology, it's in the life of marine and terrestrial organisms. So let's talk about oxygen. Oxygen content is highest at the surface. This has to do with the organisms, with photosynthetic organisms that need light to survive, right? The process of photosynthesis, a little bit of light, a little bit of carbon, a little bit of water. Next thing you know, you have oxygen. So, okay, we've got oxygen that comes from that dissolves from the atmosphere. We've got oxygen produced by phytoplankton through photosynthesis. There's an oxygen minimum layer where there's the minimum amount of oxygen, and then it stays pretty constant at depth, and it's pretty low. If we go to this graph of dissolved oxygen, right, varying, we can see that oxygen is highest in that upper reach, the upper kilometer. This is also known as the photic zone, the area where light can penetrate down into the oceans, and it decreases. There's much more life, especially life that needs oxygen, in the shallow surface of the ocean than at depth. If there isn't enough oxygen, then it creates conditions: hypoxia, low oxygen; anoxia, no oxygen. And if we have these hypoxic conditions, it can lead to mass die-offs, which is no good for anybody. It creates dead zones in the oceans. We'll talk about them. Not good. We want to avoid them. They're environmental catastrophes that we can actively mitigate through our own actions. Okay, so oxygen is important. Different organisms need it. Carbon dioxide is important in so many ways. So there is low amounts of carbon, lower in the surface, but then photosynthesis consumes that CO2, right? That's why it's lower at the surface, and it increases with depth. Okay, there's respiration of marine organisms. There is an increased solubility of CO2. The relative distribution and proportions of carbon in the oceans, but carbon has a much bigger story. It's way more exciting than this. So CO2 dissolves in seawater from the surface, and then it reacts with water to form carbonic acid. This carbonic acid can then dissociate into bicarbonate, leaving a hydrogen ion. It can also lower into or dissociate into carbonate, which will deposit in the ocean floor as rocks remaining trapped in the geologic record. This is a sink or a reservoir for the biogeochemical cycle of carbon. It can also produce 2 hydrogen ions. So most carbon in the oceans ends up as bicarbonate. This bicarbonate is taken up in the shells of marine organisms, both macroscopic and microscopic. Now, the proportion of hydrogen ions that's left over, this is going to affect the pH, which is measuring the hydrogen ion concentration. If it's below 7, it's acidic. If it is above 7, it is alkaline. There are hydrogen ions in all liquids. Distilled water has a neutral hydrogen ion concentration. Our blood is slightly alkaline at 7.4. Seawater is roughly 8.1. Acidic things we know about: lemons, oranges, tomatoes, coffee, alkaline, cleaning solutions, bleach, soap, ammonia. And so the variation, right, is hydroxide versus hydrogen ions in solution, measuring those. Okay, so how do we get on pH? What the heck is going on here? Why is this even important? Well, the oceans have a pH, and the pH has to do with the amount of carbon that's being deposited in the oceans. Now, whatever is happening with the carbon in the oceans is buffered, keeping the oceans from becoming too acidic or too basic. This regulates, it creates a stable environment in the Earth's oceans, and that stability is necessary for life to exist. It is the stability of temperature and salinity and pH that created a hospitable environment for life to begin and also for life to evolve into the beautiful diversity, the biodiversity which we have today. So, oceans buffer carbon from becoming too acidic or basic. But fast forward to today, and we'll talk a lot about this, but we cannot talk about chemical oceanography without the discussion of ocean acidification, which is the addition of CO2 lowering the pH of water. This red line is the Keeling curve. There is a site on top of Mauna Loa in Hawaii that measures atmospheric concentration. It's been doing this since 1955, and those measurements, direct measurements, show an increase, and it varies by winter and summer, an increase of atmospheric CO2. Also, with an increase of atmospheric CO2, there's an increase of oceanic carbon. With that increase of oceanic carbon dioxide, there's an observable decrease in ocean pH levels. So it's not that the oceans are acidic, it's that the pH is lowering. They're becoming more acidic. They're developing towards that end because, and we'll save this conversation, but essentially the burning of fossil fuels puts more carbon dioxide into the atmosphere than would normally occur. More carbon in the atmosphere means more carbon in the oceans. More carbon in the oceans means more chemical reactions, creating more bicarbonate with more hydrogen ions, which in turns affects marine organisms such as corals, shellfish, and marine phytoplankton. This is the base of primary productivity. The base of the food chain is the small photosynthesizing cyanobacteria and algae that are in there. They're amazing. They're microscopic. They produce calcium carbonate shells that they get from the ocean. So if we have a decrease in ocean pH, right, then essentially what happens is our bicarbonate and our calcium and our carbonate switch, and they flip, and this throws the entire system out of whack. So the short of this is This is a big environmental problem. Too much carbon dioxide in the atmosphere, too much carbon dioxide in the oceans. The carbonate buffering system of the oceans starts to get thrown out of whack, affecting marine organisms, which the problem here is what happens when we cross a tipping point, which is a concept of Earth system science, where you don't really notice the effects until it's too late, and then, oh no, what are we going to do? So if we already use the precautionary principle, then we can understand how systems work. We can make decisions now to regulate policy in regards to the environment, to protect marine and terrestrial ecosystems so that ocean acidification can halt the decline of biological systems. We'll talk a lot more about that, but that's kind of my little bit of a rant right there. The oceans are important. Okay, so last thing to talk about, nitrogen. 78% in the atmosphere, much less in the oceans, but nitrogen from the atmosphere dissolves into the oceans, and then bacteria take that N2 and they fix it through the process of nitrogen fixation into ammonium. Now, that ammonium can be converted into nitrite and nitrate. The nitrate is the key nutrient for marine organisms, specifically for producers that need nutrients to reproduce. Producers feed consumers, and when they decompose, there's a process of denitrification, which takes the ammonium, takes the nitrate that's in consumers, converts it back into nitrogen again. So, wow, the oceans are so amazing that they have the ingredients and they can switch from one form to another, from carbon dioxide to bicarbonate, from dissolved nitrogen gas into nitrate, and then cycle these nutrients back again. These are called biogeochemical cycles. They're fascinating in how they move elements and compounds and nutrients around the earth. So this gives us different types of elements in seawater. We've got conservative elements, the ones whose concentration is relatively constant. Nutrient-like elements, where the distribution is very similar to nitrates. They're nutrients. Scavenged are those that react with other particles and are absorbed to the particle surface. And then dissolve stable gases from the atmosphere. And this is kind of the variability of elements that we have in seawater. So, that was a lot of information, and I really appreciate your attention, and I hope that you could absorb this. If it was too much content, watch the video again. That's why it's here for you. But in summary, the oceans are amazing, and they have a very unique chemistry that supports life, and a lot of it has to do with the water molecule and its very distinct shape and its unique properties that allow for solid, liquid, gas at room temperature, high heat capacity, being a universal solvent, less dense solid than it is liquid, and being such an extreme surface tension substance. The oceans are in balance with other Earth systems. And if the oceans are thrown out of balance because of other impacts, anthropomorphic especially, then that's going to affect not only the oceans but also everything on Earth. And in this way, the oceans are an early warning sign. If we look to the oceans and we see, things are happening in the oceans, then you better believe that things are happening to the Earth system in general, because oceans are very resilient. They have a system of balances that have been around for billions of years and will continue to help persist for billions of years into the future. The health of our Earth truly lies, and this is a big take-home message from the entire lecture, the health of our Earth truly is reflected in the health of our oceans, and we can look to the chemistry of the oceans as a way to monitor that ocean health. So, thank you so much for your attention. Thank you for being here, and have a great day.